So today we're going to talk about in-situ visualization with ParaView Catalyst2. And if you have any questions, feel free to unmute yourself or put them into chat. So Marie is monitoring chat and she will pass any questions to me. Yeah, so it's supposed to be fairly interactive, and I think we'll probably likely run out of time. So I'll probably take a little bit longer than 50 or 60 minutes, but we'll see where. So I'll put the most important things at the beginning, and then towards the end, I'm hoping to have a demo of ParaView Live, but that might actually take a little while. So we'll see how fast we go. Anyway, so let's begin with Catalyst. So today we're going to talk about in-situ visualization with ParaView Catalyst. And the problem we're trying to solve is that large numerical simulations on supercomputers, on HPC clusters, can produce a lot of data. They can produce huge amount of data, right? And so it's been a problem for quite a few years, actually for several decades, to write all these data to disk, right? Because you can compute data, a large arrays much faster than you can save them to disk. So for this reason, the I/O, so writing data, especially three-dimensional data, many variables to disk, has really been a challenge in modern supercomputing simulations. And usually what people do is, instead of writing, for example, every time step, they write every 10th or every 100th time step, which is a very common practice, let's say in galaxy formation models or in fluid dynamics models. You simply cannot afford to write all variables at every time step to disk, because otherwise, your I/O, even parallel I/O, is going to consume more than 99% of your code's runtime, right? Another solution is, instead of writing data, every 5, every 10, every 100 time steps, you can write, just selected variables. So typically modern, let's say, CFDs, fluid dynamic simulations, they have a large number of variables. So instead of writing all these variables, you just write, a couple of variables to disk, and then you use them for visualization. So in-situ visualization is meant to solve this problem. The idea is that instead of writing full three-dimensional variables to disk, you only write a subset of these variables. So perhaps you write some simpler derivative variables, like instead of full three-dimensional variables, you store two-dimensional polygonal isosurfaces that are used to draw, isosurfaces later on in let's say inside ParaView, or maybe you're writing images directly from the simulation code, right? So this is called in-situ visualization, sometimes also referred to as co-processing, because what you're trying to do is you're trying to produce, some simplified data sets, smaller data sets, or perhaps images, graphics, movies, at runtime inside the simulation. So you might ask, wait, so we've been doing this for a very long time. So in fact, if you go back 40, 50 years ago, this is the standard way you would do output in a simulation code. So back in the 70s and 80s, people certainly could not write out, full two-dimensional and three-dimensional variables to disk. So they would typically instrument their code and put some, some graphics routines to output simple images. Using, for example, I'm back in in the 80s, I used something like pgplot in Fortran. That was great at the time, right? So what we're talking here with in-situ visualization is actually different. It's simulating your simulation code, but the idea is that instead of just doing simple plots, coding simple plots inside your simulation code, what you're doing is you modify your simulation code to expose any data structures. Typically there's a three-dimensional arrays, let's say, containing distribution of density, temperature, pressure, et cetera, et cetera. So you expose these arrays to the Catalyst library, right? And so you do it once, you modify your code once to expose all these three-dimensional arrays to Catalyst, hopefully without duplicating these arrays in memory, creating new arrays. So hopefully you just pass the description of these arrays, essentially pointers, to Catalyst at runtime, right? And then Catalyst at runtime will, apply some analysis or visualization pipeline to it. So you instrument your code once to expose data, simulation data, live simulation data to Catalyst without writing this data to disk. And then your next step is you're using familiar interactive Catalyst Python pipelines to process this data in some way, maybe to generate a simpler data set or generate some images or movies, right? So this is what in-situ visualization refers to. So in the ParaView ecosystem, there is a library called Catalyst, and that's what I'm going to talk about today, but it's not the only in-situ visualization library. So in Visit, those of you familiar with, the modern large-scale 3D scientific visualization landscape know that there is, in addition to ParaView, there is a similar package called Visit, well, a competing tool called Visit, that also has an in-situ visualization library called LibSim. And then there are a bunch of other libraries that I'll mention in the very last slide that do similar things. But anyway, today we're going to talk only about ParaView Catalyst. So Catalyst was first developed a number of years ago, so maybe 7-8 years ago. And it was developed with, so the idea was that researchers, so people who were running and writing simulation codes, they would modify their simulation code to put in the Catalyst, Catalyst function calls, basically to map their data to VDK data structures, right? So the problem here was that it was actually quite difficult to do. You had to be very familiar with the VTK data model, and it was quite difficult to do because different VTK objects were mapped in memory differently. They were using different initialization routines, et cetera. So it was fairly easy to create bugs, and also it was fairly easy to create memory leaks, which is obviously bad, for simulation codes with large data arrays. And also another problem with this approach was that the VTK code base is continually evolving. So that means that your simulation, you instrumented code, you put in the Catalyst library function calls, and then a year, 2 years down the road, the library would change. VTK library would change, Catalyst library would change, and then you would have to redo your coding again, which is not great. So Catalyst2 that came out a couple of years ago was designed to address precisely these issues. So Catalyst2 is actually instead of using VDK data structure for a user, for describing data by the user, by the researcher, it uses what is called the Conduit API. So Conduit is a library for describing data on multi-resolution three-dimensional meshes that was developed at Lawrence Livermore National Lab. And basically, it's a framework for describing multi-dimensional arrays on meshes without actually copying these arrays to the Catalyst library. So Catalyst2, the new version of the Catalyst library, uses a Conduit mesh description. So we will see this in several examples later on today. And the nice thing about this approach is that actually there is not a single Catalyst library, but it was split into two pieces. There's a core Catalyst API that is, so the API functions that we are using, as users, as researchers, they are relatively stable. So there's supposed to be, to be stable, for 5-10 years. So you instrument the code once, and hopefully this instrumented code will continue working with future versions of ParaView. And then there is also the implementation, right? So there's a combined ParaView Catalyst API that includes the core Catalyst library, plus the a specific implementation of the Catalyst API that can change. So that should not require you to modify your code. And so the implementation that we're going to use today is is supplied by ParaView itself. So if you download either binary ParaView or the source code of ParaView, it will contain a large number of Catalyst-related libraries. You will see them today. We'll be using them a lot today. And so these libraries, this is a specific implementation of Catalyst supplied by ParaView, right? And then there's the core library that you're calling from inside your code. Anyway, so we'll work with the Conduit mesh description later on. So I'm going to show you many examples, but we're actually going to start with a much simpler example where the simulation code is actually represented by, is mimicked by a Python mini application. So this application will act as a simulation code. And so I will show you some examples where hopefully you'll get an idea of how ParaView Catalyst works. So in the second part of this presentation, I'm going to jump to an actual C code. So I modified one of the examples, and I'm going to walk you through the code and show you how the Catalyst and Conduit API actually works in this context. And then if we have time, so I'm going to show, in part two, I'm going to show demos or locally, and maybe if we have time, I'll try also to show you a remote demo where I run a simulation, a parallel simulation on a cluster, and then I will use these. Well, I put in. I use in-situ visualization inside the simulation, and then hopefully, if we have time, I'm also going to talk about ParaView Live, and we'll demo ParaView Live as well. Okay, so if there are no questions, let's start with a basic ParaView Python script. So those of you who know ParaView, who've been using scripting in ParaView, you will see the script and you will immediately understand what it does. So those of you who are new to Python scripting inside ParaView, let's just walk through the script. So what the script does, this is the entire script right here. So what the script does, it loads everything from a ParaView.simple module, all functions. One of these functions is a wavelet. So this is equivalent, calling this function is equivalent in the GUI, in ParaView GUI, to going to sources and then calling the wavelet source. So you create a wavelet source, right? And then you pass this wavelet source to a filter, slice filter. So basically you're slicing this wavelet source going through, the origin 000, which is not mentioned here, it's just the default value. And then you're slicing it with a plane, and then the normal to the plane is going to be 001. So it's going to be perpendicular to the z-axis, right? Then you turn on visibility of the slice object. So basically, you make sure that it's visible in the pipeline, in the visualization pipeline, and then you issue reset camera call. So I use it here because it's actually a very convenient function to make sure that everything that you visualize fits into your current view, right? So very simple script. So let me just run the script. So here here the script, I call it sample 3A. So I'm actually going to show you the script here, sample 3A, right here, exactly the same script I showed you before. So there's nothing Catalyst related here. It's just a basic ParaView Python script. And then to run the script, I'm going to use an alias. So here I'm running this locally on my MacBook. I have ParaView 5.10.1, so the latest official stable version of ParaView installed. And then I'm going to be calling the ParaView application from inside this folder. So I'm going to say ParaView. ParaView --script is equal to, and then I'm going to paste the script to it. So this is going to launch ParaView, and then it will run the script and then show the result inside the visualization window. So as you can see, we're looking at the 3D view, but actually the object we're looking at is a two-dimensional mesh, right? Because we created a wavelet, then we apply slice, and then we visualize this mesh. Okay, so everything makes sense, right? Any questions? Okay, so let's try to use the same script in the ParaView Catalyst context. So the idea with Catalyst is that you run a simulation code, you instrument your simulation code to pass data inside a channel, a named channel, and then this data will be picked up by the Catalyst Python script, right? So what I'm going to do is, instead of in this very first example, I'm going to use a mini application. So it's actually a Python module, this Python module that will act as a simulation code producing some time variable VTK image data set. So VTK image refers to a Cartesian mesh. So what we're going to do is we're going to run this application. It's a ParaView application, but think of it as a simulation code, right? It's just a very simple example of simulation code that is actually coded as a Python module. So we're going to run it for 3 time steps, and then we need to pass data from these simulation code. So here's my simulation code. We need to pass it to Catalyst, right? So what I'm going to do is I'm going to run the script that you saw on the previous page with one modification. So previously, here's actual modification. So what I do, I take the script from the previous slide, and then instead of saying wavelet, just calling a blank wavelet source, I'm going to call the same wavelet function, but now inside the argument, I'm going to pass this registration name wavelet1 argument. And so what this does is it will take the data from the Catalyst wavelet channel, well, actual data channel called wavelet, right? This is the name of the channel, and then it will use this data for processing. So, and the data, why does the data go into this channel? Well, so inside the mini app, inside these pseudo simulation code, the channel is not named. It's just, it doesn't have a name. But you can actually assign a name. So let's assign name wavelet1 to the channel, right? So the data is produced by this mini application. We're going to take this data and put it into the channel wavelet 1. And then inside the Python script that we're going to supply here as sample3b, we're going to take this data, so the data from the channel wavelet 1, and then we're going to do some processing through this data. Okay? So the command that I'm going to do is, well, I'm going to run the script sample3b.py. And so the only difference, again, is just one line modification. So in fact, I can actually show you the difference between the codes sample3a and sample3b. You see, it's just one line that we modified. So we added the argument. Now we're taking data not from the wavelet, but from inside a named channel from the where data flows from the simulation code at runtime to our Python script. So let's just run it. So the way I'm going to run it, I'm going to say pv batch minus m ParaView demos wavelet mini app. So I'm running these minus m means it's a Python module, right? That acts now as a simulation code. Then I'm going to supply a script to it. So this is going to be my ParaView Catalyst script, which is, once again, very similar to the previous script with just one modification. Then I'm going to say script -- script version 2. So that means that inside the mini app is actually going to use a Catalyst2 library as opposed to Catalyst1 library. I'm going to run it for 3 time steps, and then I'm going to take the data and put it into the channel called wavelet 1. So let's just run it and see what happens. All right. So as you can see, it ran for 3 time steps, right? You saw some output, so time step 1, time step 2, and time step 3. But nothing was written to disk. So it ran successfully. Well, it gave some warning messages. It gave some, some output, right? So we know that it ran successfully, but it did not save any data. All right. So let's try to actually save some images. Now what I'm going to do is I'm going to take the previous script, and then I'm going to modify it. I'm going to add these lines to it. So I'm going to import a function for printing some information. So print info from the ParaView module. Then I'm going to get the current view. So get active view grabs your current view. And then later on, we can use it to save an image, right? And then we define a function catalyst execute. So this function, what it will do, it will take our view, and then it will print some information, and then it will save this view into an image that will that is named output some digits.png, right? And so this catalyst execute function actually appears once, right? So let me show you the script. So the script is going to be called sample3c. So here's my entire script. And so this is the stuff I added in the latest version of the script, right? So here I define this function only once, but you will see that actually for each of the time steps, I'm going to be creating a new image. So this catalyst execute function is going to be called at every time step of my simulation code. All right, so let's just run it. So it's very similar to the previous command, except that now I'm running the script sample3c, so the one you see on the screen, and I'm going to run it for 10 time steps. Okay, so when I run it, the data, the images should be saved into these files, output some digits.png. So let's try it. All right, so let's do ls -t. The most recently created files will appear here. So let's see what these images, what these images look like. So output something.png. Open on a different screen right here. So these are the images that were created by the catalyst execute function inside the Python script. So notice that here I did not do any modification, did not modify the simulation code, right? The only modification I made was just change the Python script itself that I passed to the simulation code. All right, so here for each of the 10 time steps, I get some image, which is a slice, right? So it's a 2-dimensional image. All right. Any questions? So this function, this function catalyst execute was run at every time step, right? Once at every time step. So everything you put into this function is going to be executed by Catalyst at runtime while the simulation code is running. So once again, it's taking data from this channel, wavelet 1, and then it applies a slice to this data. So it takes this data, right? So here's the handle for this data. Then it applies a slice to this data. And then here it visualizes the slice, right? And then it gets an active view, so the current slice view. and then it uses that view to save it as an image at a resolution 1000 by 1000. So in fact, if I check the file sizes of these files, they're all 1000 by 1000, right? So great. Okay, so you can also have a catalyst_initialize and catalyst_finalize functions, and these are called ones. So at the very beginning of your ParaView, Catalyst, script execution, and at the very end, right? So the previous guy, this guy is called at every time step. Those two guys are called at the very beginning and at the very end. So I'm not going to put them into the code, but you get the idea. Now, of course, what you really want to do, you want to create this visualization interactively, not just have some pre-programmed script, but you want to create an interactive visualization. And so this is where we're going to talk about extractors. So it's a much better way to output images and data in Catalyst. So the idea is that you add what is called an extractor, either an image or a data extracted to your ParaView Python script. Right, and that will create various, it will expose various data structures to the Catalyst library, and then will trigger various functions that will be executed every time Catalyst executed is called from the simulation code. So typically, this happens once every time step. Okay, so what I'm going to do is let's actually start ParaView GUI from scratch. So here I'm starting ParaView GUI. And then here I'm going to go to sources and create wavelet. So I'm going to search for a wavelet source, right? I'm applying a wavelet, okay? Then optionally, I could rename the input. So right now the input, the source is called wavelet1, but I'm going to use this wavelet1 because this is what we're using in our script. But in the simulation, it would be important in an actual simulation where you're running, let's say, C or Fortran code and produce some data. You have to make sure that this source actually has the same name as whatever channel name you use in your simulation code. Right? So in the pipeline browser, let's apply a slice and then an image extractor. So here I'm going to apply a slice to my wavelet. So let's apply a slice. Let's apply a slice, let's say, perpendicular to the z-axis. I'm going to have 1 here, and then 0, 0, like this. I'm going to say apply. So here's my slice. Let's hide all those lines so that I see only the slice, right? And then let's apply what is called an extractor, an image extractor. So in ParaView, I'm going to go to Extractors, and then Image, PNG. So apply an image extractor to my slice. Right. So what an image extractor is, it will actually create a function inside my Catalyst script that will write this image to disk. Okay. And the next step, I'm going to go to File, Save Catalyst State. I'm going to save it to a script called extract-image. So File, Save Catalyst State. Inside the, let's say I'm working inside. Let me actually find this directory. I'm working inside this directory. And then I'm going to save it to extract-image.py script, right? So I'll just use the defaults. For now, these are not important for now. I'll just accept the defaults. And so what this did, actually, if I do ls-t, you'll see there's a new file, extract-image.py. So if I show you what it looks like, well, there's actually a lot of stuff. But basically, it takes data from this wavelet1 source, wavelet1 channel, right? And then it processes the data, so it applies a slice to it, and then it does some other stuff. And then towards the end of the script, I have an extractor. So here I have an extractor, which is a PNG extractor. So extract an image out of this data set, right? And then save an image to a disk at this resolution. So of course, you can modify this. Let's say if I want to change the resolution, actually, let's do this. Let's change the resolution to, let's say, where is it? To instead of having 1900 by something, let's do, I don't know, 800 by 800. So our image is smaller. Right? Okay. And then let's actually run the script. So what I'm going to do is I would call PV batch, one of the previous commands. But now let's actually run it for 3 time steps. But now, so my script is called, so the script that I just created is called extract-image.py. So let's run it. So here we're we're running our simulation code, right? This is mimicking the simulation code. Then I'm passing the script to the simulation code, run it for 3 time steps, and hopefully it produces some data. So let's see what happens. All right, so it ran for 3 time steps. ls-t, it created a new directory called datasets. So what's inside datasets? Let's check. There are actually 3 images. So let's try to visualize these 3 images to open them. Oops. Again, it opens here. So these are the images that were created by my script. And actually, the colors are off, and so I would need to, insert, setting the data range properly, making sure I zoom in on the region. But you get an idea. So I could actually use the image extractor to output some data live from my simulation code. So actually, let's run a clean example. So the clean example I created before this presentation is just the example that is a modification of my previous script. So the latest script I had was sample 3B. So now the script is going to be called sample 4A. And what the script does is, so what I do here is I take the previous script I showed you, in one of the previous slides, and then remember this catalyst execute function that was run at every iteration at every time step inside my simulation code. So now what I'm going to do is I'm going to replace this function in the Python code by an image extractor, right? So I'm going to have these, so saving images at 1000 by 1000 resolutions. Actually, let me show the resolution of these guys. So the ones I just created were 800 by 800, exactly as I specified in my Python code. But let me run this simpler script. So here I have a simpler script where I'm going to run the script sample for Api. So let me show you what this script looks like. So here's my script, right? Now you see that at the end, I don't have catalyst execute function. Instead, I have an image extractor, the save an image each time step at 1000 by 1000 resolution as a PNG file. So let me just run this. I'm going to cycle up to PV batch, and then I'm going to run it for 3 time steps. But now my file is called sample4a.py. Sample4a.py. So here we go. It ran, and then it produced new images. I will open these images here. All right, here they are. So now, everything looks nice. Well, at least it fits into the current view, right? Now, you can also apply
so, Alex?
Yeah, question?
Yeah, you have a question in the chat.
I think
the question is, should we've done a reset camera there? Yeah, we can do reset camera. So reset camera, just make sure that your view is fits into the your data set fits into the current view, right? And actually have a reset camera here, right here in the latest script, right? So I visualize the slice and reset the camera to make sure that it fits into the current view. So there is reset camera there. Yeah.
Thank you.
All right. Okay, so let me show you an example of a data extractor. So a data extractor, the idea is that in Catalyst, in addition to writing images, you can also write data. So let me show you an example. So here I'm going to delete in the previous interactive pipeline, I'm going to delete the previous extractor, image extractor. And then I'm going to click on a slice, but this time what I'm going to do is I'm going to go to Extractors and then apply a data extractor. And there are a few file formats available to me here. So what I want to use is VTP. VTP stands for VTK partition data. And I will explain why it is partitioned later on when I show you Perl example. So save as a VTP file. And then I apply the data extractor. Right, and then I'm going to go to File, Save Catalyst State, and then inside the same directory, I'm going to save it as extract-data.py. Oops, data.py. Okay, just accept the defaults. Now you see that the latest file is really this extract data. And if you look at the file itself, let me just do a quick cut on it. You see that towards the end of this file, I have the data extractor now. And so this is important that I apply the data extractor to the slice, not to the wavelet, but to the slice. So here I have the wavelet, information flows to the slice, right? And then from the slice, information flows to VTP. So to the data extractor, right? So I apply the extractor to the two-dimensional slice, not to the original three-dimensional wavelet, right? And this is exactly what you see in the script, right? So here I apply the data extractor to a slice, and then this gets written to inside the datasets directory, this will be written into slides underscore some numbers dot pvtp. So that stands for Perl VTK partition dataset file format. So let's run this. Let's run the script. So all we need to do is just bring up one of these guys. And what I'm running is now the script is called, actually, I'm going to run the script sample 4b, not the one I just created, but the one right here on the slide. So, but it's the same one. So here I create an image extractor from a slice, and then I write it to these files on the disk. So the file is called sample 4b, right? The script is called sample 4b. So let me just modify it right here. So now instead of writing images, we're actually writing data. All right. So it runs for 3 time steps. Do ls minus t. You see that things went into this directory. It was modified last. So, and now we have actually these files, slice, slice. There are three. So there are 3 top level files. These are XML files. And then they actually reference, the data sitting inside these directories. But if you look into one of these directories, you will see there is just a single file because we ran our simulation in serial, not in parallel. So if we were to run this in parallel, there will actually be a separate output file for each CPU core participating in our simulation run. Anyway, so let's just load one of these files. So I'm gonna, into ParaView, I'm gonna start from scratch, and I will navigate to these files. So inside datasets directory, I have these slices. Let's just pick one of them. And then here's my slice, right? So here the idea is that I was loading not an image, I was loading a data file, right? But this data file, once I load it into ParaView, it will show it as a 2-dimensional image, right? So here, in fact, it's called wavelet, but if you go to information, you will see that it's a 2-dimensional image. It's not, there's no 3rd dimension, right? And this is because the data that I was saving from Catalyst was a 2-dimensional data. It was the slice, right? So in fact, in my visualization pipeline, if I were to apply the extractor not to the slice, but to the original data set, then it would write a 3-dimensional data set, right? So it's completely up to you what you do, right? Because in my Python Catalyst script, I applied the data extractor to a slice. It created a 2-dimensional image, right, as opposed to a full 3-dimensional data set. And inside the same simulation code, you can have as many extractors as you want, right? You can have any number of image extractors, any number of data extractors, right? And then for each extractor, typically a file or series of files will be saved to disk at each time step. Right? So this was a very simple example with the mini app, right? Now let's take a look at an actual simulation code. So when you run a simulation code instrumented with Catalyst2 library, you actually have to install a bunch of components. So obviously you have to download and compile Catalyst2 code yourself, right? And also you need to compile, well, you need to have the runtime implementation, right? So typically people use ParaView, ParaView, and it has, an installation of ParaView that has some Catalyst library related files. And so you have several options here. So you could, and the manuals actually mention this, that you could download the binary distribution of ParaView and use it as a runtime ParaView Catalyst implementation. But actually, I highly recommend that you don't do this because you will likely run into problems. And the problems are related to the included MPI version. So basically, a precompiled ParaView includes its own MPI that is typically not compatible with MPI used on a cluster, right? So what you really want to do is you really have 2 options. So the 2 options are either you can use a module, a ParaView module that we have many different versions of ParaView installed on the cluster, or even better. So this will give you much smoother ride. You can compile ParaView yourself and then use the self-compiled ParaView as the runtime ParaView Catalyst implementation library. Right. So actually put so if you follow my slides, so the link in the slides that you can find in the chat, there are 2 links here. So one is to the slides and the other one to the zip file with scripts and instructions. So they actually have a file that tells you exactly how to install all of these components on one of our clusters. So actually I have an example on Cedar, but it's exactly the same on all other Alliance clusters, right? So you compile the Catalyst library, you compile ParaView server, and then you basically use this, at runtime to run your Catalyst instrumented simulation code, right? So for this demo, I'm going to show you next is I'm actually modified a C example code from Catalyst examples. So Catalyst examples actually sit inside the ParaView source file or ParaView binary distribution. So if you download the latest official stable ParaView 5.10.1 and unpack it, you can go into examples, Catalyst2, make sure you don't go to Catalyst library. You have to go to Catalyst2 because they're totally different. So the library was completely rewritten a couple of years ago. And then there's a bunch of examples for C and, well, actually one example from C and half a dozen examples from for C++. So I took one of the C examples and I modified to simulate this data, right? So this is a simulation code that now simulates the data. And what this data is, actually use it a lot in teaching visualization, teaching ParaView. It's called a three-dimensional sine envelope function. And it's just, it has some very characteristic look. And I also made it a a time-dependent function. So for time evolution, I simply shift the function along the x-axis with a periodic boundary conditions. And the function is defined inside a unit cube. So all x, y, z go run from 0 to 1. And also inside the same zip download that you can access from the link that I have, I showed you before. So once you download the zip file, unpack it, you will find a standalone MPI-MPI directory. We actually have two examples there. So I have two versions of this code in C code. One is where I put data as a Cartesian mesh. And in the second example, I output data as a VTK unstructured grid, right? So VTK unstructured grid is useful if you have more complex cells than just a Cartesian mesh. But I have two versions of the code, so you can play with both. Both of them should work, right? So typically, how you would use this? Well, you would go into one of these directories, either unstructured data directory or image data directory. You will compile the code. So there's a make file included as well. And of course, you will need to install all the components. You'll need the Catalyst core library and the runtime implementation for this to work. Then you have to modify the make file, obviously, to point so that this make file points to the right libraries and include files. And then once successful, once you compile it, you run the simulation code, and then optionally you can pass various flags and parameters related to Catalyst stuff, right? So this is the way you run in serial, or you can run in parallel, right? So in this case, you'll just say MPI run minus MP number of cores, and then the same stuff. Okay. So in these, so let's actually take a look at this example. So I'm going to show you the unstructured data example that is slightly more complex. So I'm going to go into standalone, and actually instead of the MPI version, I will go, because I'm going to run it now on my laptop that does not have MPI installed. I'll just go not into MPI directory, but into a standalone directory without MPI, so just a serial code. And so here's the data. So here's the code, the entire simulation code. And actually, I probably want to delete all these. Well, I won't delete them. I will override them, the Python scripts. So, but to compile it, I will need to, I say make. So basically what it does, it compiles my simulation code and it links it to the core library that I have installed here. So here is the core Catalyst library, right? And then at runtime, I need to set up a couple of variables. So Catalyst implementation paths that points to my runtime Catalyst implementation, which in my case is actually sitting right here. Oops, standalone ParaView, yeah, ParaView right here, right? And so here, actually, at runtime, we'll be using a bunch of Catalyst libraries that are sitting here, right? And then there are several files here. So the main loop of the simulation is, and actually intentionally, I keep all the original file names and function names so that you can actually compare them to the other examples in the Catalyst manuals. So the main loop of the simulation is actually fed_driver.c, and this is what it looks like. Actually, I can show you with bat fed_driver.c. So here's the main loop of the simulation. And here at the start of the simulation, we call the Catalyst initialization function, right? Which I will show you in a second. Then we have a loop, so the time loop right here. Time step goes from 0 to some number, and then inside the loop we call the do Catalyst execute function, right? So all these functions are defined inside my simulation code elsewhere. I'm going to show you in a second. And then at the end of the simulation, I call the do Catalyst finalization function. And so these guys actually define inside what is called the Catalyst adapter. So the Catalyst adapter is the main file that you modify if you wanna modify the data description that is passed to Catalyst. Right? So here we have these three functions that I showed before in the main driver. Do Catalyst initialization, that does something, right? Then do Catalyst execute. So here into Catalyst execute, I actually pass a description of my data. Right? It's actually fairly long. Pass description of my data to Catalyst. I'm going to come back to this in a few minutes. And then we have the Catalyst finalization. And the data itself is actually defined in this other file, fed data structures.c. I just want to show you quickly where the data is defined right here. So here, basically, I have I go through all cells, all three-dimensional cells, and then for each cell, I go through all vertices. So each cell is basically it's a hexagon, or similar to a cube. It has 8 vertices. So for each cell, I go through all vertices. I compute the average of X, Y, Z coordinates of all vertices. So that will give me the geometric center of the cell, right? And then I use this geometric center of the cell to define my function. So this mathematical sign envelope function that you saw in my slide a few minutes ago, right? So here where stuff goes into the density array, and then this density array is actually being described to the Catalyst library at runtime. So here's the density array, and then here I have the description of this array, right? But basically, I'm exposing the density array to the Catalyst library, right? So I'm not creating any new arrays. So at runtime, Catalyst library will have access to all information stored inside this density array. All right. So to actually run this on a cluster, to run something like this on a cluster, you would there are a bunch of ways you can go about it. So in this example, I load, so I compile everything with GCC. I also need the OpenVTL library and module, sorry, and the ParaView off-screen module. And the reason for this is, so in this example, I'm using in this slide, I'm using the precompiled ParaView module. So I'm loading these two modules, this one and this one, so that I actually have access to environment variables that I will need for compilation and for, well, especially for runtime, right? So for these variables and this variable, so they needed to compile the code and to actually run it. But the important thing I want to stress here, and this is really, really important, is that when you start running a Catalyst instrumented simulation code, it actually does a lot of I/O to load, various library components, and it tends to do quite a lot of I/O at startup. Right? And so for this reason, I actually discourage people to run Catalyst on a parallel file system. So of course, never any, it applies to any simulation code, never run anything out of home directory, right? So you really want to run things out of scratch. But with Catalyst, you have to be careful. I discourage you from running things on scratch because it's going to be very slow. Because at initialization, as I said, you need to load, your code needs to load a lot of components, various libraries. And it'll be very, very, very slow if you try to do it even out of scratch. So for this reason, what I suggest to do, for real production codes is what you do is, let's say you want to compile, you want to use the runtime, you want to use the ParaView module, ParaView off-screen module, but then you still need to, to have your simulation code, right? And then you need to have the core Catalyst library code. So what I suggest to do is you can compile both inside the /tmp directory on a login node. So on login node on a cluster, a /tmp directory refers to a RAM disk, right? So compiling things on a RAM disk is fast. So you do it on a login node. Don't run the simulation code there. Just compile the Catalyst library and then your simulation code. And then take these files and put them into a tar file, for example, gzip tar file. It could be in your home directory, it could be in Scratch, anywhere else. And the point here is that at runtime, when your simulation job starts, you go into a temp directory. So now at runtime, this temp directory is not the same as, so this /temp is a RAM disk on a login node, right? So once you start your simulation, you start your job, go into this temp directory, which is typically a local SSD, local to a node where your job is running, right? One of the nodes participating in your run. And then into this temp directory, which is a local SSD, so it's going to be much faster than the parallel file system. You unpack your code along with the Catalyst library. And then you go there, optionally you can recompile the code itself. But the point here is that you work not off a not off a scratch file system, but you work off a local SSD, and this is going to be much faster for initialization. So trust me, this is going to make a huge difference. And then so you compile the code, and then you set up, the couple of variables pointing to the runtime ParaView Catalyst implementation, and then you run the code, right? So you apply, you run the code. Here's my code. I run it in parallel, and then I supply some script to it. Okay, so this is what I'm going to do. I'm going to do the same, but I'm going to do it on my local laptop and not in parallel, but in serial. So in my laptop, I'm actually going to go, I'm already in the directory, right? So I compile the directory, right? Compile the simulation code. And then I already have, I believe, the proper catalyst variables. Yeah, I have this guy. So yeah, it points to the runtime ParaView Catalyst implementation. And then all I need to do is just run my code. So I'm going to say that, right? So if I do it like this, it runs in this case for 5 time steps. Well, why 5 time steps? Because in the main driver code, I have 5 time steps here, right? So it ran it for 5 time steps, but actually didn't, it wrote something to the terminal, but it didn't produce any data. So in fact, if I do ls-t, there's no data produced, right? So to actually produce data, well, you can, if you want, run a ParaView Catalyst script. So the way you would run the script is you would, run your simulation code, and then you would pass a script to it. So it'll print some information to the terminal, but actually won't output any data. And the reason for this is, so it basically, prints, some bounds and some very basic variable information for two variables, velocity and density, but it's actually it's not writing anything to disk. So in fact, if I check my file system, nothing was written to disk. And so the reason for this is because we actually need to have an extractor in our script, right? Either an image extractor or data extractor in the script, right? So remember how we created an extractor before. Before with the mini app and with the wavelet source, we went into the GUI, then we created the wavelet source from scratch, and then we used it, to process data in some way, and then we applied an extractor to it, image or data extractor, right? But the point here is that we need to load something into ParaView GUI that we would call representative data set. So a representative data set must be of the same data type as whatever you generate in the channel and pass into, to the Catalyst library, right? So exactly the same data type, exactly the same attributes, meaning exactly the same set of variables, essentially, right? And type of variables. So how do you do this? You need a representative data set. So before, with simple wavelet, it was really easy because we can go to source and we could create it at runtime, right? So now we cannot really do this very easily. So there are actually a number of options. And so in the previous version of Catalyst, actually used to be a function called readWriter.py that you could pass to the simulation code at runtime, and it'll just generate data, full data that was received inside the data channel. So the data went from simulation code to Catalyst, and all this data was written to disk. So there is currently in the works a readWriter.py for Catalyst2, but unfortunately, as far as I know, I tried to use it. It's not yet fully developed. It doesn't function properly, right? So there are 2 other ways to create a representative data set. So one is basically try to do it through a combination of sources, perhaps programmable sources and calculators. It's straightforward, but it's very tedious, right? So the other way is to actually modify your simulation code to write this data by hand yourself. And there's actually one example. So if you go to the image data example, so that's the Cartesian mesh example for Catalyst2 in C++, there's actually exactly the recipe for doing this. So I put this into my simulation codes, into my C, image data and unstructured data simulation codes. And so the way this is done is through the Conduit nodes that I mentioned in the introduction. So how do you pass data from the simulation code to Catalyst? Well, this is done through what is called Conduit Mesh Blueprint. So the Conduit library from Lawrence Livermore National Lab is used to describe data inside the Catalyst core API, right? So this is done via the so-called Conduit node objects. So these node objects, so actually the whole Catalyst library was coded in C++ and actually has a C++ API. So if you do it in C++, it's actually the most elegant way, right? Unfortunately, our simulation code is in C, so I have to, do this from C. You can do it in a number of ways. I will show you the simulation code in a second. But basically, the way this do it, you create these Conduit node objects that are lightweight containers with hierarchical data construction. So you can have nodes inside nodes, right? So the top level node named Catalyst load is used to load a specific Catalyst implementation. If it's ParaView Catalyst, then it looks for a top level node called Catalyst. So we'll see this in a second in the simulation code. And then there are a bunch of things you can pass to, for example, you can pass a script, the name of the script that you're supplying to the simulation code at runtime. You can create some special pipelines. At execution, at each time step, you can pass the time step, the time, channel name. We're going to call it grid. The channel type is going to be well, in ParaView Catalyst is either mesh or multi-mesh. We're going to use a simple mesh, just a single mesh, and then also you will have data stored on top of this mesh. So actually, let me show you what the simulation code looks like. So I'm going to go to BAD and Catalyst adapter.h. So here at initialization, remember that this function is run at the very start of my simulation code, right? So I initialize the Catalyst interface, and then here I can pass the scripts. Well, actually here it creates a node. So here I create a node Catalyst load, right? So here is a node, well, actually it's called Catalyst init params, right? And to it, I pass a node called Catalyst load, which points to ParaView implementation. And then here, so these are the lines that I added myself to the simulation code. And what these lines do, they actually create a special pipeline. So this is done at initialization. This pipeline is created at initialization of type IO, which simply writes all data in the channel call grid to a file supplied by the argument, right? Okay. So this is done, this node is created at initialization, but it's actually used. So this pipeline of type IO is used at execution time, is used at once at each time step, right? And then, so here's actually how data description is done. So data description is done via these nodes as well. So here I create a conduit node, Catalyst exec parameters, to which I write a bunch of things like the cycle number, the current simulation time, coordinates, the mesh topologist is going to be an unstructured mesh. Here are my coordinates that are actually taken from a runtime simulation arrays. And it's going to be an unstructured mesh, so I need to supply the connectivity as well. So basically, connectivity array. So this array stores the IDs of the cell that are part of each hexagon. And then on top of these guys, I have, so on top of vertices, I have a three-dimensional field called velocity. It's somewhere here. I don't see it right now. Right here, velocity. And then on top of each cell, I have a 3D field named density right here, right? So here's my density array, which is, it's not copied to Catalyst, it's actually exposed to Catalyst, right? So data is still sitting in the simulation array at runtime. And anyway, so this is how you pass the data to Catalyst, right? And then how to use it. So remember, the problem was to actually create the representative data set, right? So in order to create a representative data set, what we need to do is, so here's my code, and I'm going to say bin, run the code, and then I'm going to say -- output. Actually, I need to go to my notes. So let's see, -- output. And then I'm going to use this format to write our data into files dataset -some numbers.vtpd. Okay? So here we go, ran for 5 time steps, and the data actually went into these files, right? Now I can actually load these files into ParaView. Then I can create scripts. Catalyst scripts with either image or data extractors or both. And then I would run this to actually do things at runtime. And unfortunately, so I covered something like 50% of material, and I'm already very close to the end of this presentation. So what I'm going to do is I will show you the demo of the full pipeline. So starting from the representative data set, right? And then using this representative data set to create a Catalyst script, and then using this Catalyst script at runtime to output image data. And then we'll pause there for questions, and then if there is interest, I can actually show you the the ParaView live interface in the last section. So let's just do this complete pipeline. So here we created the representative data set, right? And next step, I want to create a Catalyst script out of this representative data set. So I'm going to start from scratch. I'm going to navigate to this folder. So it's inside datasets. Oops, no, it's inside here. It's inside standalone unstructured data. So right here, these guys. So let me just load one of these guys. apply. So here's my data set. And what I want to do is I will resample. So because this data is unstructured, I cannot apply Conduit filter to it. So it's grayed out here, right? So I need to resample this data to a Cartesian mesh. So let me do this. I'm going to go to resample to image data, resample to image right here. And then I'm going to do 100, 100, 100 cube. And then to this cube, I'm going to apply a Conduit filter. So I'm going to do density at some, intermediate value, a Conduit filter right here. All right. And then I'm going to do an extractor, an image extractor, PNG, save it to a file. And then I'm going to file, save catalyst state. And I'm going to call it, so inside unstructured directory, I'm going to call it extract dash image.py. So because I applied an image extractor right here, override it. Yes, override it. Use the defaults. And so here I created the latest file. So here it is. This file, I'm actually going to use it as a runtime ParaView Catalyst script, right? So the way I use it is I will now simply run the simulation code, and then I will pass this file to the simulation code. So it will run again for 5 time steps because this is what was coded in the main driver C code. So it runs for 5 time steps. But most importantly, for each time step, it will output an image. So ls-t, images went into this datasets directory. Let's check it. Oops, datasets. Right here, these are the images. Let me show you the images. Oops, datasets directory. So here are the images that were created at runtime. And as you can see, there's some time evolution, right? So there is, you see motion with periodic boundary conditions along the x-axis, exactly what I coded in my simulation code. So similar to this example, so this is, I just showed you the complete pipeline, right? So run the simulation code with dash output, with these flags to create a representative data set, then load this representative data set into ParaView, create a ParaView Catalyst script in the GUI interactively, and then copy it to the cluster, and then run the simulation code passing the newly created ParaView Catalyst script to this simulation code. So this creates at runtime datasets directory in which you find images from your simulation data, from your simulation run, right? And of course, if you, instead of creating an image, in the image extractor, if you apply a data extractor, that would save the data to disk. Okay, so I'm going to pause here for any questions. I know this is a very advanced topic, so I try to, unfortunately, 1 hour is just not nearly enough to cover this, but I hope to also show you the ParaView live demo. So, but I pause for any questions before I go there. So yeah,
I have
please
a
go ahead.
question, and maybe this is what you're going to show us in ParaView Live, but I think I have the impression that Catalyst gets used with like a simulation that's running for days, and you open the program and you can get visualizations as they arrive, as they finish in the simulation. Okay, cool.
So no, I mean, so yes, you can do that, but that's not the best usage actually of this. So the best usage to do everything in batch mode. So the idea is that you run the simulation code in batch mode, and then you take whatever was written to disk, whether it's simulation or image, whether it's data or images, right? And then you use them, to create your movies or process them with post-processing, right? But you would still run the simulation code as a batch code, right? And the reason for this is because, well, actually, I'm going to explain this in a minute. Because ParaView Live, it's both dangerous and it can waste enormous amount of resources if it not do it accurately. So, but I'm going to talk about it in the next few minutes.
Could I just jump in with a question there? So one of the things I was thinking about was using Catalyst for debugging. So one of the problems, for instance, say running huge fluid dynamic simulations, sometimes you can have complicated geometry in the mesh. And this can cause your simulation to blow up in particular areas. Could you use Catalyst to try and catch where your residual errors are starting to blow up? And then
you can do it live. You can do it live while the simulation code is running, and that was called ParaView Live. Yeah, so that's the next session.
Well, that'd be very interesting. Very useful.
Any other questions related to what I've just talked about? So not ParaView Live, but what I've shown so far. And I understand, so this is the top of the hour, so if you have to leave, we're recording this, so you can actually watch it later on. If you have to leave, you can do that, but I'm hoping to, next I'm gonna show you the ParaView Live demo. Are there any other questions?
I guess I was going to say, if we watch the rest of this and we do have questions, how would you prefer us to ask, over email, or do you have drop-in hours that we can join in?
No, email. Yeah. So if you go to the very top, very first slide, here's my email. Just send me an email, and yeah, I'll answer.
Yeah, and I just pasted in the chat the email that goes to the both of us as well.
Wonderful. Okay, thank you so much. Yeah, I'll definitely be in touch.
Sure, no problem.
All right.
Yeah, so let's talk about ParaView Live for a few minutes. So the idea of ParaView Live is to use the same pipeline to actually connect to a live simulation code and then visualize or explore the data in your simulation code while the simulation is running, right? So that's why it's called ParaView Live. So the idea is that you would run the simulation with a specially designed script where the Catalyst Live option is enabled, right? And then you would pause your simulation, and then while the simulation is paused, while the arrays are static, so to speak, you can explore them in ParaView. And so your ParaView, so the idea is that, so normally when you talk about remote ParaView, client-server ParaView, typically the ParaView application that you have on your computer is a client, right? And then the server is running remotely somewhere. So in this case, it's actually opposite. So the client is going to be the simulation code, and the server is going to be your ParaView GUI, right? So your ParaView GUI is going to act as a simulation server to which your simulation code is going to connect at runtime, and then inside the server you will be you're using the GUI to actually explore live data. So, but anyway, what you need to do is, well, actually, so this is there are several caveats that are very important to know. So one of them is that whenever when you enable the ParaView Catalyst Live option inside your script, inside your Python script, what happens is the only thing it does is it will expose all data structures inside Catalyst to your interactive ParaView pipeline, right? So not just whatever you were saving with Extractors, image or data Extractors, but everything inside Catalyst, available to Catalyst, will be exposed to you, right? And then you can optionally click on, enable some data, but be very, very, very careful with this, because this can actually, completely saturate your network. Because if you try to debug a large simulation code, and you're talking about large live three-dimensional arrays that are sitting in memory, on an HPC cluster, and you try to debug it. So if you try to, visualize, to import these three-dimensional arrays into the ParaView server, your network is going to be saturated, because so let's say you have 10 terabytes, 100 terabytes of simulation data in large code. Obviously, there is no way you can ship these to your ParaView ParaView running on a laptop, simply because, well, it's just way too much data, right? So instead of shipping three-dimensional data, what I suggest is create some derived data sets, and you can do this easily inside the ParaView Catalyst script, right? The way I've shown you before. So you apply various filters, and these filters will also be available to you. And make sure that you enable only data, derived data, not the original three-dimensional arrays, but derived data, right? Well, unless your arrays are very small and, it's very easy to ship them, something like 100 cube obviously can be shipped fairly easily. But anyway, so let me show you a demo. But for this demo, so I'm going to run the demo locally. But for this demo, I actually need to enable Catalyst Live option when I save the script, right? So what I'm going to do is I'm going to go back to this. And so here, here I apply an image extractor, right? Actually, yeah, this is good. I apply an image extractor. And then, so the next step would be to go to File, Save Catalyst State, right? So I'm going to save it as Extract Live. But this time, so yes, override. This time, I'm actually going to enable the Catalyst Live option. So it's right here, enable Catalyst Live, right? And the only thing it does, it will expose all other data structures available to Catalyst to your ParaView server, right? So I'm going to do this, and then I'll say OK. So now I have the code that is called Extract Live, right? And if you look at this code, you will see that there is one thing that is different now, that you have this live. Let's see where it is. Inside the extractor, you'll have this live somewhere. live flag. Oh, right here, yeah. Right here, yeah. You have the live flag, right? Which will expose all other data structures. Okay, great. So now I have this script that I'm going to run. But before I do this, I actually have to prepare. So because now my ParaView application will act as a server waiting for incoming connection, I actually have to enable it, right? So I'm going to start from scratch. And then I'm going to go to Catalyst, connect. So this will start listening on a given port. So I'll just use the default 2222, but obviously you can use any reasonable port that is open on your computer and or on your network. So I'll say OK. So now it says accepting connections from Catalyst coprocessor, basically from a live simulation on this port on my computer. Okay, great. And the next thing that I must do, this is very important, is you're going to go to Catalyst and then pause simulation. Okay, so that your simulation doesn't fly, in a few seconds or in a fraction of a second, because I want to pause at the first time step, and then I want to explore the data that Catalyst will have access to at the first time step, right? So simulation is not running yet. So all I did was enable listening inside ParaView to the simulation data, Catalyst data on these on port 2222. All right, so and now I'm going to run the simulation. So to run the simulation, all I need to do is just the same simulation, and then I'm going to pass the extract live script to it. So I'm going to do this, and then hopefully it will connect. So let's see. Yep, and it connected. So it paused at the first time step, and now these are the data structures that are available to me, right? So this is very important, and this is where you can run into trouble if you try to import the wrong thing. So right now my simulation is very small, so I can actually afford to import the three-dimensional data set. So grid is a three-dimensional data set. So grid is actually the regional data in the Catalyst channel, data channel, before I apply any filters to it. And then I apply a couple of filters in this script, in the extract live script. I apply a resample to image filter, right? So if I enable this guy, resample to image, it will also ship the three-dimensional data, which is large, right? And then I apply a contour filter, which is, if your simulation is very large, then contour two-dimensional data set is going to be much smaller than three-dimensional data set. So once again, grid is three-dimensional, resample to image is three-dimensional, whereas contour is two-dimensional, right? So if I want to be careful, I want to click on this guy. So I enable this guy, I enable the contour. So when I do this, the contour data is going to be shipped from the simulation, sent from the simulation over the network to my ParaView server, to this guy, right? And then I can actually exploit. So now it's available to me here. I can actually enable the view. And here's my contour at time step 0. And so this is just a data object inside the pipeline, right? So I can apply any filters to it. So for example, if I want to apply a Glyph filter, I can certainly do this, right? It's just an object, right? Just a data object. So here's my two-dimensional data that I can, process in any way I want, right? So if you want to go to the three-dimensional data, well, either the original unstructured data right here, or the unstructured data resampled at 100 cube to Cartesian mesh is this one. So if I enable one of these, it's a three-dimensional data set that is going to be shipped to my ParaView, right? So for small data sets, it's no problem, right? So right now I can actually do this, but obviously for very large data sets, be very, very, very careful with this because you will saturate your network very easily, right? So I can actually take the three-dimensional data and then I can visualize it. So here's my three-dimensional data. Actually, which one of them is three-dimensional data set? Yeah, so this guy is a three-dimensional data set, right? And so this guy is, let's see, what's that guy? Oops, I'm not sure which one that corresponds to. But here I'm looking at three-dimensional data set, right? Whereas here, if I enable, let's see, this guy, where's my two-dimensional view? I lost it. Yeah, I'm not sure it. Yeah, it's okay. Yeah, I don't see the two-dimensional view, but now I have access to the three-dimensional data. But the point here is you can enable, any data stream from the Catalyst channel, right? And it'll just ship only that data inside, to your ParaView client. So be very, very careful. Another thing you have to be aware of is that right now my simulation is paused, right? It's paused at step 0. So that means that if you're trying to look at the data from a very large simulation, if you pause the simulation, right now my resources are, my core CPU cores are sitting idle, right? And obviously if you're talking about very large simulation, your cores will be sitting idle. So be careful because you can waste a lot of resources, right? So for this reason, actually, yeah, for this reason, and also the fact that you have to be super, super careful not to ship, large three-dimensional data sets. That's why I'm very cautious about using ParaView Live. So it's a great tool. It's a great tool for debugging, but it's really meant for, debugging, exploring data set, probably on a smaller scale, but it's not great for live production, right? So for live production, use, what have I described in the previous section? Okay, hopefully that makes sense. So how would you use ParaView Live on a simulation cluster? Well, here's actually, let's see. I had a slide for detailing exactly, exactly that. Yeah, so here's how you use it on CETA. So on CETA, it's actually a little bit tricky, and it worked not every time. And I think the reason for this for me was because the ports can actually be busy, or some network along the way. It's either the academic network around CETA, or maybe your ISP, et cetera, could be blocking the ports. So you have to be careful. You have to make sure that those ports are available both on your side and on the cluster side, and also there are no firewalls blocking. But the idea is fairly simple. So typically you would start by you prepare your simulation code, right? So here I start in this case an interactive job. I go to a local SSD, right, into which I unpack my simulation code along with the Catalyst library. I go into the simulation directory. I compile the code, right? Then I set up the path to the ParaView Live ParaView Catalyst implementation, right? But I don't start the simulation code. So the next thing on my computer, the next step is I set up reverse SSH port forwarding. So in this example, I assume a local port ending with 3. So this guy is a local port. The one with ending is with 5 is a remote port, right? So I organize reverse port forwarding. And then optionally, I might need to clear some local ports. Obviously, not being sysadmin on the cluster, you cannot do this, but you can do this locally if your local port is busy. And then you would launch a local ParaView GUI, go to Catalyst Connect, go to Catalyst Post Simulation. Right now, it's waiting for incoming simulation data, and it will post the simulation at the first time step. And then it will then basically you will start your job. And then you will wait for connection to be established, and then you explore your data interactively inside your ParaView GUI. So that's it. As I said, for me, it worked maybe one of my 10 attempts was successful, and I think it has to do with basically ports and firewalls, but it should work in principle. So if you run into problems, let me know, and I can help you. So anyway, so that's all I wanted to show. So once again, ParaView Catalyst, really fantastic framework, can be used not just from C. Well, it's actually a C++ library. I showed you examples in C, but it can be used from other languages as well. So people use it routinely from Fortran, from Python. I also saw some examples. Somebody wrote a Julia interface. It has been shown to scale to millions of CPU cores, so it can actually be used at very large scale. And the design philosophy is you use this API through Conduit nodes to expose simulation data to Catalyst library without duplicating any data. So this is very important because we're talking about huge data set sizes, very large arrays. So you have to be, you cannot afford to duplicate any data. So and that's exactly how Catalyst was designed. So use Catalyst2, not the original library, because the Catalyst2 is much better. And be careful when doing anything in ParaView Live, because you can waste a lot of resources and you can saturate your network fairly easily if you're not careful. And there's an official Catalyst users guide that comes with any installation of ParaView, but it's not any installation. When you download the source code of ParaView, on the same website where you download ParaView from, you can also download the official Catalyst users guide. And now if you go to the latest page for ParaView, you will download the official Catalyst users guide for ParaView version 5.10.1, but it's actually not up to date. So be careful, because in most places it actually refers to Catalyst 1. Whereas the title of the users guide was updated, its content was not really updated everywhere. So be careful. And so the very last thing I want to talk about, there's another project. There's an In-situ project called Sensei that is maybe 5-6 years old. And so here the idea is that instead of using a single interface like ParaView Catalyst, for processing your data, so Sensei library is a more universal library that sets communication between a data producer, which is a simulation code, to a generic in-situ endpoint. So this in-situ endpoint could be ParaView Catalyst implementation and ParaView library, Catalyst core library along with the ParaView Catalyst implementation, could be the visits libsim library. There are a number of other endpoints, YT, for example, for Python processing of multi-resolution data, et cetera, et cetera. But the idea is that it's supposed to be a more universal interface. So Sensei is it's a library, right, that you can call from your simulation code. And then there's also an XML file. You modify this, you modify your simulation code once, you compile it. And then if you want to switch from one endpoint to another, you don't even have to recompile your simulation code. You simply update one of the XML files in your setup, and it will talk to a different endpoint. Obviously, you have to have this endpoint installed and be functional, but yeah, it will work. So I played with it a little bit. It's great, but really for simple use, I recommend ParaView Catalyst interface and the original implementation that I described in this webinar, unless you have a reason to go to Sensei, which is a more universal approach.